You're watching a Channel 98 NBISD TV production.
How y'all doing today? Welcome to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, and I'm enjoying a nice little sampling of some chocolate vanilla swirl soft serve yogurt. Yes, indeed. It's really, really good. Pardon me here. Now, you're probably wondering what this has to do with the show. Well, actually nothing. It's just good stuff, and I'm kind of hungry. I'm just teasing. Actually, today's show is going to involve a little bit of yogurt mixing. That's going to be at the end of the show. So it's going to be kind of intriguing. If you like ice cream, you like yogurt, and you want to know how to make the perfect blend, why don't you stick around today and watch the episode with me. Download those worksheets from the district website at www.newbraunfels.txed.net. Grab a bowl of ice cream next to you and work some problems with me today. What do you say we get started? Let's do it. Lesson number 7. We're going to look at linear systems in 3D. So these are going to be coming at you, almost popping out of your television set today. Now, what is 3D in the context of the real world? Well, it's where we live. We have planes that we walk on in 2 dimension, and we also have a 3rd dimension, which is kind of the elevation. If you've ever used a global positioning system, a GPS system, it actually gives 3 coordinates that help you to identify anywhere on Earth that you happen to be by giving you the latitude, the longitude, and the elevation. So this idea of a 3 coordinate system is something that is used on a daily basis to navigate through our 3-dimensional world. Well, any point in a 3-dimensional coordinate space can be represented then using an ordered, not an ordered pair, but an ordered triple. Okay, there's 3 of them. And we're going to write it in the form X, Y, and Z. We have this new letter Z now. Well, the Z-axis is going to be another axis that's going to extend out perpendicular from our old coordinate plane. So it's like coming straight out here from the origin. So if you look at something like this, this could be kind of a little cross-section of an office building. This is in 3 dimensions. We're going to have a plane, which might be the floor. That would be the green thing here. And then we're going to have a wall on either side. So this is 3 planes, the green, the red, and the blue. And notice that where they intersect right here, that's going to be the common point for all 3 planes. Well, we're going to draw that over here as a 3-dimensional coordinate plane system. And it's kind of like our old X and Y axis, but we got this thing coming in here diagonally. Now, it's always kind of difficult to represent a 3-dimensional product on a 2-dimensional flat surface. So we're going to have to do our best here to imagine. We actually changed the notation a little bit. We're going to call this still the origin, and coming kind of out of the paper, you can imagine that. That's going to be our x-axis in the positive direction. And then we're going to have our y-axis in the positive direction going to the right. So this will be our y-axis in the positive direction. And then the positive z-axis we're going to have coming straight out. So those are the 3 positive coordinates. Notice that they do extend on the other side. Those are going to be the negative coordinates. And I'll draw those kind of as a dotted line. Sometimes if we're sketching points, we're just going to maybe draw the 3 positive versions so that we don't confuse ourselves with all the lines on there. But it's very important to understand here the orientation. We've switched it a little bit. We've got X and Y. That's kind of like the floor. And then we've got Z, which would be the vertical rise in an adjoining wall. So that would be a 3-dimensional coordinate plane. Let's go ahead and try plotting some points now. Okay, so on this coordinate plane, we actually have our X, Y, and Z axis drawn again. And I've got it marked off. And we're going to go ahead and plot this first point. It's the ordered triple 4, 6, -4. Well, remember, the first is our X, the second is the Y, and the third is our Z. So what this means is we're going to start at the origin, and we are going to go 4 units on the positive x-axis. 1, 2, 3, 4. That puts me here. So I've gone this way. And then from there, I'm going to go on the y-axis 6 units in the positive direction. Now here's what's kind of hard. We're kind of tilted here. So as I count 6, I want to try and keep this distance in between the tick marks, but I have to start from here. So 1, 2, 3, 4, 5, 6 puts me right there. So I've gone down the x-axis, and to the right, which is here. And now finally for the z, I have to go -4, which is down 4. So that's going to be 1, 2, 3, 4. Move down this way. And there, in fact, is the ordered pair, or the ordered triple, sorry, for this point right here. It's kind of like going along one wall, going out in the middle of the room, and then going down into the room below. Okay, let's try another point here. 3, -2, 5. I'll do this one in purple. This one is 3 on the x-axis, so 1, 2, 3. I'm here. That's -2, so I have to go left 2. 1, 2, and then +5 is up 5. So from there I'll go 1, 2, 3, 4, 5 up here. And I'll draw a little line, and then once I'm where I'm at, where I need to be, I'll put a solid dot. So I've gone down the x-axis, to the left 2, and then up 5. And there we are. And one last point just to get a good feel for it. Let's look at the point -5, -5, 0. So along the x-axis now we have to go back 5 units. 1, 2, 3, 4, 5. That puts me here. So I've gone this way. And then -5 on the y, that's to the left. So I'll go 1, 2, 3, 4, 5, somewhere in there. And then finally go up 0. Well, I don't have to go anywhere. There I am. So it's going to be a little bit strange and uncomfortable to do this. But the more you do, the better it's going to, you really get used to it actually, okay? Practice, practice, practice. Again, it's trying to visualize a point in space on a two-dimensional surface, which can be difficult. Okay, let's see the consequences of that. In the previous episode, we were solving linear equations. So recall that a graph of a linear equation in 2 dimensions on a coordinate plane is a straight line. Well, in 3-dimensional space, the graph of a linear equation is not a line, it's up 1 dimension, it's a plane. No, not that plane, a plane, like a flat plane surface, like this sheet of paper. Now, because a plane is defined by 3 points, in order triple, we can graph linear equations in 3 dimensions by finding the 3 intercepts, that is, the points at which it crosses each of the x, y, and z axes. All right, let's give this one a shot. We want to graph the linear equation 4x plus 8y plus z equals 2. All right, so there's 3 variables x, y, z. I have my x, y, and z axis labeled here, but I have nothing scaled on the x, y axis. Well, to find what the graph looks like, which is going to be a plane, we want to find the intercept. So let's go ahead and find right here the x-intercept first. Well, to find the x-intercept, it's the point along this line here that the graph crosses. And notice any point along this line, we're not going to be out along the y-axis, so that's going to be 0, and nor are we up or down on the z-axis, so that's going to be 0. So to find the x-intercept, we're going to let the other 2 variables, y and z, equal 0. Well, if you look at the equation then, if I let y equal 0 and z equals 0, I just have 4x equals 2. So now that I have 4x equals 2, I can solve, divide by 4, and I get x equals 2/4, which is 1/2. So I'm going to draw 1/2. I'm going to call this point 1 unit, and so 1/2 would be right there. So that's going to be the x-intercept. Now I'll do the same for the y-intercept. Well, on the y-axis, we're going to let the other 2 variables, x and z, equal 0. And if you go back to the equation, if x is 0 and z is 0, I just have 8y equals 2. So 8y equals 2. Now I can solve, and I get y equals 2/8, or 1/4. So again, I want to keep my scale the same. So if this is a 1, a 1/4 is, there's half, it's half of a half. So it's going to be right in here somewhere. And then finally, to find the z-intercept, where it crosses the z-axis, the z-intercept, same procedure. I let the other 2 variables, in this case x and y, equal 0. And if I go up here to the equation, if x and y are both 0, I get 0 plus 0 plus z, or just z equals 2. Well, that was easy. There was nothing to solve there. So I'm going to keep my scale the same. There's a 1, there's a 2, and I get that point right there. So let's go ahead and list these points now as ordered triples. The first one I found was the x-intercept. So that was the point 1/2, comma 0, 0, as an ordered triple. This point here, the y-intercept, was the point 0, comma 1/4, comma 0. And then finally, the z-intercept was the point 0, comma 0, comma 2. Now, I have 3 points that lie on different planes. Those actually define a plane. Let's go ahead and connect the dots to make our triangle. And I'm going to use a straight edge here, a unicorn straight edge. Those make the best kind. So from this point to this point, I draw a straight line. From here to here, another straight line. And then I'll connect these two with a straight line. Now notice I have made a little triangle. And if you want to envision this, it's kind of like taking a triangular piece of board and standing it in the corner of a room, where one edge is on the baseboard on one wall, the other one's on the baseboard on the other wall, and we're leaning the tip up against the corner there. That's what it looks like. Now that right there is just a piece of the actual three-dimensional plane. That is the graph of the linear equation. The actual plane itself extends out. And if I try to draw it, I might mess my graph up. But it looks something like this. And it's basically spreads out in all directions to infinity. So you could think of maybe the actual plane setting flat on this triangular board that's stuck in the corner. And if it rests flat up against it, then that plane would extend out in all directions. Here's a little bit better way to visualize it with a little bit better colorization. It's that right there. This orange region is actually going to be the plane that we just talked about. So again, that is what the graph of the linear equation in 3 dimensions looks like. It's not a line, it is a plane. Okay, so what we're going to do now is we're going to actually work with equations in 3 dimensions. Just like we solve systems of equations in 2 dimensions, now we're going to also solve systems of equations in 3 dimensions. Now remember that in order to find a unique solution or unique solutions to any system of equations, we need as many equations as we have unknowns. So in 2-dimensional space, we had 2 unknowns, we needed 2 equations. In this case, we're going to have 3 unknowns, we're going to need 3 separate equations. Just as the point of intersection of the 2 lines in 2 dimensions gave us the solution to a linear system, the point of intersection of the 3 planes in 3 dimensions is going to give us our solution to the linear system. Now, how many solutions can there be? Well, we can actually have 0, no solutions, 1 unique solution, or infinitely many solutions. So here's what some of those look like. The no solutions, it could take on one of 3 different forms. I can have 3 planes, the red, blue, and the green, or the blue, red, and the green, that are all parallel to each other. They don't intersect at all. Remember, to be a solution, it has to be a common point of intersection for all 3 planes, which means in this example, I have the green intersecting the blue and the green intersecting the red, but I don't have all 3 intersecting at the same place, so this would also be no solutions. Over here, I have a nice little construction project going on here. Looks like a little A-frame, but there's no common point of intersection among the 3 planes. I have the green and the red intersecting, I have the blue and the green intersecting, and the blue and the red intersecting, but at no point do I have all 3 intersecting at one point. So this would be 3 different versions of a no solution to the system. Well, the one solution case is, again, the cross-section of that apartment or office building. I've got the blue, the red, and the green, and they're all slicing through each other at a single point right there. And that point would be the unique solution, the order triple, x, y, z. And that's going to be the most common type that we come across. But there also could be infinitely many solutions in this little gear or flywheel example, where we have the red, the green, and the blue, and they're intersecting all along one of their edges. So in this case, they don't intersect at a point. This whole spine right here is a common point of intersection, which is a line, and they coincide at every single one of those points. And because a line is made up of an infinite number of points, this would be a case where there's infinitely many solutions. Okay? So, to solve an algebraic 3x3 system, how do we do it? Last week we looked at 2 methods for a 2x2. We looked at elimination, or linear combination, and substitution. The method of choice that I'm going to be using this time is elimination. And how do we use elimination? Well, we're going to be able to draw on skills that we previously learned on the last episode for 2x2s. All we're going to do is we're going to have to add more steps. So first we're going to reduce the 3x3 system to a 2x2 system, and then we're going to solve it like we did on the previous episode. All right, let's take a real quick short break here to enjoy some public service announcements and some more of that yummy, yummy, delicious yogurt soft serve. But while you're gone, think about this. What do you get when you cross 13 hospital patients with 13 more hospital patients? The answer, when you get back.
So you used to be taller. What happened?
What happened? Pressure. The pressure to be so cool and so popular and to never say the wrong thing to anyone, so I'm cool with everyone. The pressure to drink and get high. pressure happened.
So now what?
I don't know, but this isn't working.
Hey, welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, enjoying some yogurt today. Glad you could come back with us. Did you think about the answer to that question? What do you get when you cross 13 hospital patients with 13 more hospital patients? Might be in there because they've eaten too much yogurt. Well, the answer, you get 26. Back to the math. Let's look at this little system of equations. Notice that the brace signifies a system of equations. And we also have three variables, x, y, and z, x, y, z, x, y, z. So three equations, three unknowns. This has a unique solution if it has any at all. Okay, so the first thing we want to do is make sure that our equation is written in the proper sequence. So alphabetical order is a typical way to go. Notice I have x, constant, y, z. So what I'm going to do is I'm just going to rewrite this entire system and I'm going to write them all in the same order. So that's going to be a 2x minus y when I bring it across plus 3z equals, I'm going to get my constants on the right. This one would become x plus y, that already looks good, minus 2z equals negative 7. And then over here I'll get 3x plus 2y minus z equals negative 7. So that I have my x's, my y's, my z's all vertically stacked, and then I have my constants separated on one side. Now let's go ahead and give these equations names, 1, 2, and 3, so that I can refer to them. What we want to do is try to eliminate a variable. I have 3 of them, so I'm going to have to eliminate one at a time. And just like on last week, we're looking for nice coefficients that when I add or subtract will give me a 0 pair. So notice on the y's right here, equation 1 and equation 2, I have a negative 1y and a positive 1y. So if I add equation 1 to 2, I'm going to be able to eliminate the y's. So let's go ahead and do that. I'll show that right here. I'm going to take equation 1 and add it to equation 2. So to write that out, I get 2x minus y plus 3z equals 4. And then the other equation, x plus y minus 2z equals negative 7. And since they're opposites already, I will add them. So here I go. 2x plus x is 3x. Negative y plus y, by design, that's 0. And then I get 3 minus 2. That's going to be 1z, or just z. And then I get 4 minus 7 is negative 3. Well, that gives me one equation, but I still have two unknowns. So I'm going to call that one equation 4. Why not? All right, well now, since I've eliminated the y's, I need to keep that theme going so that I want to get another equation with just an x and z. One of my equations up here is going to be the pivot equation, which means I'm going to have to use it twice. But I have to get all 3 involved. I've already gotten 1 and 2 involved, so I somehow have to get 3 involved, which means I'm going to have to get rid of this 2y. I can use either one of the other 2. I think I'm going to use number 1 because the sign is already opposite. And all I need to do then is multiply equation 1 by 2 to make that a negative 2y plus 2y, and I'll be good. So here's what I'm going to do. I'm going to multiply the number 2 by equation 1, and I'm going to rewrite equation 3. So that's going to give me this. I'm going to get 2 times 2, which is 4x. 2 times negative y is negative 2y. 2 times 3z is plus 6z equals 2 times 4 is 8. I can multiply by any number. Remember why I did that? Well, if I rewrite equation 3, I get 3x plus 2y minus z equals negative 7. Now, since I have negative 2y and 2y, I can eliminate the variable by adding them. So that's why I did that. 4 plus 3 is 7x. Those go away. 6 minus 1 is positive 5z. And 8 minus 7 is 1. So now I have an equation of 2 variables, x and z, but I have another one up here. So I'm going to call this one equation 5. Now I can write these two as a system of equations. 3x plus z equals negative 3, and 7x plus 5z equals 1. Now this is back on familiar ground. I have 2 equations, 2 unknowns. I can use elimination, or I can use substitution. Now notice I can use substitution here with z pretty easily. I used that quite a bit on the last show, so I'm going to go ahead and use elimination here. I will go ahead and multiply the top equation. In order to get a 5, I'll multiply it by negative 5. And I'll just rewrite them out here to the side. So I get negative 15x minus 5z equals positive 15. And then I get 7x plus 5z equals 1. Just rewriting it. Now I can add them together. So I get negative 15 plus 7 is going to be negative 8x. Those go away. 15 plus 1 is 16. Oops, that equals 16. Sorry. Now I have one equation, one unknown. That means I'm making progress. I'll divide through by negative 8, and I get x equals 16 divided by negative 8, which is negative 2. Hooray! That's progress. Now, to find the actual other values, I can plug this back up into either one of these two equations. So it doesn't matter which one. I'll plug it into this one here. The numbers look smaller. So I have 3 times x, which is negative 2, plus z equals negative 3. So I get negative 6 plus z equals negative 3, and z equals, when I add 6 to both sides, 3. And now that I have 2 of my unknowns, I can go back to any one of my original 3 equations up here. It doesn't matter which one. I'll choose this one here. It looks like it's pretty easy. So it's x plus y, so I know x is negative 2, plus y minus 2 times z, which I just found to be 3, and that has to equal negative 7. Oops, there I am. I'm sorry. What I did is I plugged that into equation 2. So now if I simplify, I have one equation, one unknown, so it's going to work. Negative 2 plus y, that's going to be a positive 3. So, I'm sorry, I lost my track. Okay, here we go. So it's minus 6 equals negative 7. Negative 6 minus 2, that's negative 8 plus y. Just kind of rounding third, coming on home here. Add 8 to both sides. 8 minus 7 is 1. So I found all 3 of my unknowns, so therefore there's one solution. Those 3 planes intersect at the order triple x, y, z, which is negative 2, comma 1, comma 3. And it wasn't so bad. It's just a lot of careful record keeping. Numbering your equations is helpful. I'm going from a 3 by 3 to 2 2 by 2s, getting down to a system now of equations and 2 unknowns, and then from there we can do what we did last time on the last episode, get our single solution, and then just start plugging in backwards on the way up to get our 3 values. All right, takes a lot of practice. Now it's time for the part of the show that we call
Deja Review.
All right, now in Deja Review today, we're going to actually review the concepts in the context of some fun, yummy yogurt. So I made up this yogurt company. If I was to have a yogurt company, I would call it the Wal-May Yogurt Company. And what does Wal-May stand for? Well, it stands for the We All Love Math and Yogurt Company. See that? Well, here's what Wal-May sells. They're going to sell yogurt blends, 3 to be precise. They're going to sell a vanilla chocolate blend, a strawberry vanilla blend, double and a chocolate strawberry blend. Not my favorite, but they make it. I have the option. Now the vanilla chocolate blend we're gonna see requires 2 quarts of vanilla yogurt and 2 quarts of chocolate yogurt to make 1 gallon. 4 quarts in a gallon, right? So 2 vanilla, 2 chocolate, it's an even mix. The strawberry vanilla blend requires 3 quarts of vanilla and 1 quart of strawberry to make a gallon. So it's primarily going to be the vanilla. And the chocolate strawberry blend, which we're going to call C, requires 3 quarts of chocolate and 1 quart of strawberry, so predominantly a chocolate with a little bit of strawberry. Now, here's the parameters. Each day, this company has 800 quarts of vanilla yogurt, 650 quarts of chocolate yogurt, and 350 quarts of strawberry yogurt that they have available for making these yogurt mixtures. The question is then, how many gallons of each should they use in order to use up all their supplies? They want to be an efficient company. They don't want to have leftovers because then they might have to eat them themselves. Oh no. Okay? So that's a really good math problem that has very, very practical business implications. The best way to do this is to organize your information into a table. And the table that I have here basically has the flavors, vanilla, chocolate, strawberry, and then it has the amount needed that we need of each variety. V for vanilla chocolate, S for strawberry vanilla, and C for chocolate strawberry in quarts per gallon. And so I have 2, 3, and 0, and 800 total. I have 2 of the chocolate for the vanilla, 0 chocolate for the strawberry, and 3 chocolate for the chocolate strawberry, for a total of 650, and a 011 for a 350 total. Now, that takes a little bit of effort to organize it like that. But once you do have it organized like that, it's going to pay giant dividends because it makes the setup of the equation very, very easy. So what we want to do next is explicitly define our 3 unknowns. We're trying to find the number of gallons of each that we have to make. So I'm going to let V equal the number of gallons of vanilla chocolate, S the number of gallons of strawberry vanilla, and C the number of gallons of chocolate strawberry. Now, how do we set up our equations? Well, the column is really set up ready to go. It's going to be 2 times V plus 3 times S plus 0 times C, and that's going to equal 800. So notice that if I take the units here of quarts per gallon and I multiply it by gallons, I get quarts. And so the units of these equations are going to be quarts, which add up to the total number of quarts. So doing that, I get 2V down here plus 3S plus 0C equals 800. And the next row, I get 2V plus 0S plus 3C equals 650. And finally, 0V plus 1 times S plus 1 times C equals 350. And now I have my system of equations. Now notice in this one that I have zeros, at least in one equation. That's going to make it a little bit easier if we use the elimination method. So why don't we go ahead and try to get rid of the easiest variable. I don't know, maybe V. I'm going to use the bottom equation. So I want to get rid of V. It doesn't really matter which one. So let me go ahead and label these now as equation 1, equation 2, and equation 3. What I'm going to go ahead and do then is I'm going to I'm going to subtract actually. I want to take equations 1 and 2 and subtract them so that I can eliminate my V's. They already have the same coefficient. So I'm going to do equation 1 minus equation 2. So if I do that, I get 2V minus 2V, which is going to be 0V. I get 3S minus 0S, which is plus 3S. And then 0 minus 3 is negative 3C. And then over here I have 800 minus 650 is 150. So I get this equation, 3S minus 3C equals 150. So one equation with two unknowns. Let's call that equation 4. Now what I need to do is I need to get another one involved. And I think I can just use equation 3, right? Notice equation 3, 0 times V, 0 times anything is 0. So in this case, if I just take equation 3, which already does not have a V, to be 1S plus 1C equaling 350, I actually now have my two equations. So that actually made it a little bit easier. Let's go ahead and try to solve this now. I will try to eliminate a variable. I notice over here that I have a negative 3 and a positive 1. So it might be easier to multiply the bottom equation by 3 and try to eliminate the C's. So in doing that, I'll rewrite it. I get 3S on the top minus 3C equals 150. And on the bottom, multiplying through, I get 3S plus 3C equals 350 times 3 is 1,050. Now if I add those together, 3S plus 3S, well that's 6S. And then I get a 0 pair here. And 1,050 plus 150 is 1,200. And this is an S, not a 65. Well, now all I have to do is solve for S by dividing through by 6. So I get S equals 200. That's 200 gallons. So what does that mean? That I need to make 200 gallons of the strawberry vanilla mixture. Well, how do I figure out how much to make of the others? Well, I can work back up to this equation up here, and I'm going to choose this one. So now I know that 1 times S, or just the 200, plus 1 times C, or just C, has to equal 350. And now I can easily solve, subtract 200 from both sides, and I get 150. So I have to make 150 gallons of the chocolate strawberry mixture. And how do I find the last mixture? Well, I can plug it into either of the other two. If I want to find a chocolate, I better use one that has the chocolate in it. All right, now that we have our S and now that we have our C, all we need to do is find V, the gallons of the vanilla mixture. So I'm going to go back to one of my original equations that has a V in it and choose one, maybe equation 1. So it's 2 times V, which I'll do right here, plus 3 times S, which I just found to be 200. So that's going to be right here, 200 gallons, plus 0C has to equal 800. And now all I have to do is solve that. So 2V plus 3 times 2 is 600. That has to equal 800. So if I subtract, 2V equals 800 minus 600, that's 200. And now here we go. 200 divided by 2 is 100 gallons. And we finally have our final totals here. To use up all our supplies, I need to make 100 gallons of the vanilla mixture, 150 of the chocolate mixture, and 200 gallons of the strawberry mixture. Sweet. I hope you enjoyed that delicious episode of Deja Vu. It's Algebra 2 today. Systems of equations in 3 variables can be pretty daunting. The key is just to take your time when you're reading the questions. Read them very carefully. Figure out exactly what it is your end result needs to be, and kind of work backwards from there to try and develop a plan of action. What do I need to end up with? What do I need to get there? What does the equation or the words tell me that I can use to get to the answer? So working backwards kind of gives you an idea of how to get there going forward. Just takes a lot of practice, multiple steps involved, but you're only going to get better by working lots of examples, and you're going to get comfortable with them. I'm pretty comfortable with this yogurt. Till next time, I'm Kevin Corpy, reminding you to do your homework.